Okay, I hope you can see the shared screen.
Yes, sir.
Okay.
Yes, sir.
See, in the first question, it is related to the effect of atmosphere while transmission of energy signal, that is electromagnetic radiation. Okay. And the question is, the remote sensing can't be done at 1.95 micrometer. Okay. Wavelength, because in the atmosphere at this wavelength, if you analyze the atmospheric transmission, this the atmospheric transmission Tx, sorry, it is represented by symbol m versus wavelength. Okay, so at 1.95 micrometer, there is a valley. Okay, and it is the water absorption band 1.95 micrometer. So there could be a query like in this case, the correct option is energy is absorbed. Okay. Another query can be formed like which phenomenon is responsible for this, whether it is scattering or absorption. Okay. So in that case, you need to mention there are two major phenomena in the atmosphere that affect or that decrease the energy signal strength. So they are absorption and scattering. So at 1.95 micrometer, if you analyze the atmospheric transmissions versus wavelength curve, and 1.95 micrometer is a water absorption band. Okay, so at this particular wavelength, energy is absorbed, and absorption is the responsible phenomena in the atmosphere. Even if you notice that when we were discussing about spectral signature of a different objects, okay, so when we plot wavelength versus this reflectance curve, and if there is a moisture content present, like if in the leaves there are the moisture content, in the soil if there are the moisture content, you can see a valley at 1.95 micrometer. So this phenomenon is everywhere. In the atmosphere, there are the water molecules, H2O molecules. They trap the energy signal, and there is a kind of a resonating effect. So they do not allow, I mean, the energy at that wavelength to pass through. Even when an energy component interact with the material, certain material like leaves or soil, and if there are the moisture contents, so in that case also you can't get the reflected energy because energy is trapped, energy is absorbed by those objects. Okay. Please wait. Coming to the second problem, compute the wavelength at which sun radiates the maximum energy. Okay. So which formula we need to apply over here?
Wien's displacement law.
Correct. We apply over here the Wien's displacement law, where we calculate the wavelength, that is lambda m, and it is equal to A divided by T over here. Fine. And the value of T over here, 6000 degree Kelvin, that is the surface temperature of sun, and A is the constant. And if you place these two values in this formula, then what the value you will get? It is how much?
0.483 micrometer.
Yes, correct. This is a 0.48 micrometer. 0.48 micrometer is the correct option. The problem, this problem third, it is associated with the interaction of energy with the Earth surface object. Okay, and what is the effect of surface roughness, wavelength of the interacting EMR radiation, and at what angle of incidence that energy interact to the object. Okay, and what are their effect to decide a type of reflectance, whether it is specular or diffuse. So we have already discussed about the formula, and that formula suggests the relationship between the three parameters, that is HT is the surface roughness, then we have a lambda 8 cos theta. Okay. See how we can like analyze this problem. There is a way to understand. Let's say if you forget this formula, then how on the basis of concept you can decide like whether after the interaction of EMR, the type of reflection is diffuse or specular. So there is a very simple way. If wavelength is very large compared to the surface roughness, so it is a kind of inequality. It's a kind of a relative comparison. If you increase HT, similarly at the same time, if you increase the wavelength, what will happen? Whether it is a specular reflectance or diffuse, they maintain. In this case, and when the surface roughness is very low compared to the wavelength, do you know how we define a wavelength? If we analyze a particular signal, so there is an electric and magnetic field, and it varies in a sinusoidal form, a cosine form. So this is the wavelength we define over here, one wavelength. Okay, and HT is the surface roughness. If you see from the side view, it's a kind of side cross section. Then this tells us the variation. It's a standard deviation. If you increase the wavelength, let's say in the first case, the wavelength is lambda 1. In the second case, we have a lambda 2, that is 2 times of lambda 1. So lambda 2 is equal to 2 times lambda 1. So in this case, what will happen if you increase the wavelength? So the way energy signal change from its, the maximum in between the two maxima, upper side and lower side. Like we can say this is the upper side maxima, lower side maxima. Okay. So in between these two values, the energy signal change. Okay. If this change is slow, so if wavelength is large, this change I mean this with respect to time, this change is slow. So in that case, what will happen even at a larger HT, the specular reflection will be there. So if HT is less than wavelength, this is the condition over there and it is satisfied at the interaction point, then specular reflection takes place. Like in this case, the surface roughness is less compared to the wavelength. Okay, even this cos theta also comes into the picture over here. Okay, now to this example, why it is so? Like formula it directly suggests fine. If this if this is satisfied, then it is specular. How we can understand it conceptually? As I'm talking over here, lambda 1, in case of lambda 2, what is happening? Lambda 2 is less than is equal to 2 times of the lambda 1. In this case, the rate of change is slow. So if rate of change is slow, so it is compensated even if this standard deviation is more. In that case also, the specular reflection takes place. Like at large wavelength, that energy signal will be reflected in one direction without deviated in other directions, even at the uh, very rough surface. Okay, maintaining this condition over there. So if you get this problem, at a particular surface roughness HT is given, EMR wavelength lambda is given, and angle of incidence is given. The nature of reflection from a surface is specular. Like one set of values are given. Let's say HT1, comma lambda 1, comma theta 1. They are fixed, they are given. Okay. And with the combination of these three variables values, the surface is specular. It means this HT is less than lambda 8 cos theta, it is satisfied. If wavelength is monotonically decreasing, keeping surface roughness and angle of incidence constant. So what is happening now? This wavelength is decreasing. HT is decreasing. It's monotonically decreasing. Okay. Like you can say that you are just decreasing this wavelength. What happened? If you keeps on decreasing, then this inequality, this will change. After a certain level of change, what will happen? This will be greater than. Okay. And at that moment, at that time, what will happen? Specular reflection is changed to diffuse. It means what is happening over here, if you see this variation of energy signal with respect to time. Okay. the rate of change, it is increasing. Even further, okay. So there will be a value for lambda at which this inequality will change. Okay. So when this inequality will change, and as it is monotonically decreasing, so what will happen? The nature of reflection will change from specular to diffuse. See, it is simple inequality we have two in this problem. 2 points you need to notice very carefully. The information that is given, the lambda is monotonically decreasing. Okay. And for the first set of values, the reflectance is, the nature of reflectance is specular. So the criteria which you have to decide it, that criteria is given by this formula. So what you are doing, you are just continuously decreasing the wavelength lambda in this fashion. Okay. So what will happen? Earlier, the type of nature of reflectance till this inequality is satisfied. Please wait. Okay. So if you keep on decreasing this wavelength lambda, so you are just decreasing it. There is a wavelength value. We can say it is lambda naught. Okay. At which the ht is equal to lambda naught 8 cos theta. Fine. Further, if you decrease this, like further, if you decrease this, then what will happen? Now this inequality will change. That is ht greater than lambda 8 cos theta. For this, if I consider over here, for this entire range, and there is second range over here. Okay. For this range, we have a specular. Below lambda naught, we have a diffuse. What is a change? Specular to diffuse. Is it clear? कितने लोगों ने ठीक किया इसको? How many of you have done it correctly?
I have done correct.
Yes, sir.
I have done, sir.
Okay, fine. So I hope it is clear to all. My objective is to all of you need to understand what is the concept. Okay, if there is any doubt related to this discussion, any one of you can discuss with me right now. Okay. Okay, this fourth problem, and it is the active remote sensing systems depend on do not need any energy source, external energy source, day or night, their own energy source. So this fourth option is correct. So I think this is a simple question. The fifth one, the selective scattering depends on. So when we discussed about the scattering, so there we talk about we have a two types of scattering, non-selective and selective. In case of selective scattering, we have a two types.
Hello, sir.
Yeah, please.
Sir, in fourth question, here the first option is showing correct, and you say fourth. Their own energy source, so the correct one.
Where is what is the first option that you are looking?
Oh, sorry, sir, it's right one.
See, don't be there might be swipe in the option, like maybe you are looking one and that is fourth in my case, but their own energy source is mentioned in your case, in our case also. Maybe that option could be changed. Okay. Option could be changed means maybe in your case this their own energy same option is given A, while in some other it is given B. Okay. So the fifth problem, it is scattering, related to the scattering. So selective scattering, it is of two types. The first one is Rayleigh scattering. And the second one is? Okay. So in Rayleigh scattering, when the wavelength is very less compared to the particle size, when we say when wavelength is equivalent to the particle size, then we have a Mie scattering. So the selective scattering depends on, the first option is correct, both wavelength and particle size. Like we are using this in inequality, we are using the particle size and wavelength.
Sir, Rayleigh scattering is caused due to the tiny particles, no, sir. The diameter of the particle should be very less compared to the wavelength.
Yes, sir. Diameter is less than the lambda.
No, correct. It's not less than. It's you can correct it. When we have a large wavelength with respect to the particle size, fine. And if the wavelength is very less compared to the particle size, then in that case we have a non-selective scattering. Like when we consider the bigger molecules in the lower atmosphere, like H2 and CO2. So there we have a non-selective scattering, and that doesn't depends on wavelength. In the sixth problem, we see vegetation like trees and grasses green in color because vegetation, the correct option. So what we have discussed, like how we see the color of object. if you analyze the entire process, then what happens? Just I'm drawing over here the schematic that describe the entire workflow. Sun acts as an external energy source. In an electromagnetic spectrum, energy is transmitted by the sun, that is radiated by the sun. Okay, because sun internal temperature, surface temperature 6000 degree Kelvin. So sun radiates the energy. Somewhere here we have the earth. This is the different layers in of the earth atmosphere. This energy enters into the earth atmosphere. Okay. And if let's say some person is standing over here and we have a tree. If I zoomed in, so there is a tree and a person is standing and looking towards the tree. Okay. When we consider the sensitivity of our eyes, so our eyes are only sensitive within the visible spectrum. They are red, green, and so in our case, our eyes only sense the energy interaction within blue, green, and red. What does this mean? It means out of all other wavelength outside of this band, once they interact with our surface object, there is a reflection that is not sensed by our eyes. So when this red, blue, green, and red, these three bands interact with the vegetation over here. Okay. When these three bands interact with the vegetation, obviously there are also bands outside of visible spectrum, but they are not sensed by the eyes. Further, they are reflected back. If you analyze the spectral signature of vegetation in a visible spectrum, if you see the spectral signature of vegetation, okay, so in the visible spectrum, the highest reflectance you get in green band. Okay. So in the gridded data, when the different grids are selected from the tree, okay, so from those grid surface, the reflected energy is dominant in green band. Okay. And further, when we see the mapping of a color assignment, like the band B1, it is blue, band B2, it is green, and band B3, it is red. What happened after when the eyes sense the energy in three bands? So as I said before, by considering the spectral signature of vegetation, the highest reflectance we see at green band. So if let's say there are three energy levels, E2, E1 and E3, which one is highest? Just seeing this curve, we can say that E2 is highest. In the green, the sensor, our eyes collect the highest energy in terms of its magnitude. E1 and E2 is less compared to E3. So further, what will happen? The DN number that is assigned, and final the color assignment. So if you see the mapping for the green band, sorry, for the blue band, blue color is assigned. For the green band, green color is assigned, and for the red band, red color is assigned. So though this energy in green band is dominant, so green color is dominant, and finally you see vegetation green in color. So let's say if this problem is subjective in nature, and you need to explain it. What is the reason behind this? So all these steps you need to follow. That is expected. That is expected to be there in your answer sheet. It's not like just one line you write it. Okay, in the green band we have the highest reflectance. You need to draw this spectral signature. You need to mention that our eyes are only sensitive in visual spectrum. It discards all other wavelengths outside of visual band. Okay. Then even you need to mention that what is the behavior of atmosphere in these three bands, like the curve which tells you the atmospheric transmissions versus wavelength. You also need to mention that when we analyze the radiant exitance curve with respect to wavelength from the sun, and there we obtain the highest energy at 0.48 micrometer. All these, and it all depends like how much marks is allotted for this problem. Okay. So if you see the option, so vegetation color, you see green, absorb energy in green, blue band more than red band. It is not correct. Just you need to see the spectral signature and you will get your option. So reflect maximum energy in green spectral band within visible spectrum. So this is the correct option. Even if you see the statement, the fourth statement is correct, but not in the context of this problem. Because there is a discussion, we as a human, when we see the object, so our eyes do not sense the energy outside of the visible spectrum. Okay, but this is correct. the reflected energy in NIR band is maximum if you analyze the vegetation spectral signature. This option is correct, but it is not correct in the context of the question that is asked over here. Because in our case, our eyes discard the energy outside of visible band. Okay, so we only limit like in the spectral signature, while the analysis, if you see that this is the curve we get. Okay, so you only limit yourself to the visible spectrum. Only you need to limit to the this spectrum. Okay, though here we have a maximum, but in our case, if it is if this in the question, if it is mentioned that okay, when we see a multispectral sensor, satellite onboard multispectral sensor, in that case, what is the maximum energy that is reflected from the vegetation? So in that case, the fourth option is correct. Like in an IR spectral band, the vegetation reflects maximum energy. The seventh question, it is related to the effect of atmosphere in the energy transmission through it. Atmospheric windows are available wavelength ranges in which atmosphere, what it does, blocks the energy? No. When we see the atmospheric windows, okay, and let's say we consider it as a subjective problem. So how we can approach, how you will respond? First, you need to plot the wavelength versus atmospheric transmission curve. Okay. Then after that, you need, on the basis of this curve, you need to mention about the windows, and that can be written. The atmospheric windows are the location where let's say on the basis of this 20-30%, if it is 0 to 1, because the atmospheric transmission varies from 0 to 1, or you can say 0 to 100%. Okay. So mathematically, it can be written like you need to write the range, let's say lambda 1 to lambda 2. And when we talk about atmospheric transmission over here, so you know that what is a lambda 1? Lambda mean it can be rather. What is the lower limit? Like first we need to define the domain, and then you calculate the range for m lambda. So in this case, you write it lambda mean less than or equal to lambda, less than or equal to lambda 1. Certain values if you get that you need to mention. And we see that in visible spectrum, how much it is, m lambda value you need to mention over here. Then you need to second the second. So this range talks about the variation of lambda, where we can say the m lambda is more than 0.5, some threshold value that you need to see from this atmospheric transmissions versus wavelength curve. So the segment which you are deciding over here on wavelength axis, lambda mean to lambda 1, then lambda 1 to lambda 2. Okay. These segments talk about the atmospheric windows. Okay. And in these wavelength ranges, the m lambda value is, we can say, more than 50%. It is close to 1. And then these segments wavelength range, they are called as atmospheric windows. Okay, it means within this range, with the least energy absorption or with least decrease in energy magnitude, the energy is transmitted towards Earth's surface. So the second option is correct. The minimal energy loss. See, the minimal energy loss is defined in terms when you mention over here the lambda, m lambda value over here. If m lambda is close to 1, then obviously in this case, if m lambda is, let's say, 0.9, then what will be the energy loss in this case? 10% of the total energy. Loss is 10%, while 90% energy is transmitted and only 10% is lost. So minimal energy loss is that you need to see, it is defined. This problem number 8 is related to the thermal band. Okay. Thermal scanners are designed within 8 to 14 micrometer. Because in this wavelength range, you need to select a most appropriate option out of given 4 options. Earth radiates maximum energy. Atmosphere severely scatters and absorbs the energy. Earth radiates maximum energy. Which one is correct option? Who will tell me?
The fourth one, sir. Earth radiates the maximum energy.
Why not the second option?
Because, sir, Earth radiates the maximum energy near the visible range only.
Okay.
Near the 0.5 point.
Here we talk about the thermal scanners. So do you know thermal scanners, they sense the radiated energy component. Actually, they sense the temperature. So 8 to 14 micrometer in this spectral band, when you analyze the spectral exitance, this curve of energy radiated versus wavelength. Okay. So in that case, there is a 3 micrometer dividing line. Okay. After 3 micrometer, the Earth, it starts radiating energy. And when the wavelength increases, it reaches to its peak value at what wavelength? Lambda is equal to 9.7
micrometer, 9.7.
9.7 micrometer. Okay, so this 9.7 micrometer lies between 8 to 14 micrometer. So we can say that if you move further, so this is the range. This is the wavelength range within which the Earth radiates the maximum energy. Okay. And you write it, then what is the Wien's displacement law? What is the Wien's displacement? What is the formula?
Lambda equals to a constant A by temperature.
So lambda 1 is equal to A by T. And what is other formula that we write to determine this radiated energy versus temperature?
Stephen-Boltzmann law.
It's Stephen Boltzmann law. M lambda M is equal to sigma T to the power 4.
Yes, sir.
Okay. So based on these two formula, you will get this curve, and the energy which is radiated, it is M over here. This M is not reflected. Listen carefully. The Stephen Boltzmann law gives the value of radiated energy by a black body, okay, when the temperature is more than 0 degree Kelvin. So this M is the radiated energy. M is equal to sigma T to the power 4. In case of Earth surface, we have an average temperature considered 300 degree Kelvin. Okay. When we apply this second formula, so we get lambda is equal to 9.7 micrometer. And finally, we get this curve. So this curve is radiated energy from the Earth. Okay. And it is significant in 8 to 14 micrometer. We use thermal scanners to sense the temperature. To sense the temperature in terms of radiated energy, because see over here, M is equal to sigma 2 to the power 4. The radiated energy component is the function of temperature. Okay. So when we talk about a radiated component, when we discuss about the temperature, so there will not be the, we are not considering over here the reflected energy. What we are considering, Earth radiates the maximum energy. This ninth problem is the energy reaches to the sensor in optical spectrum. Optical spectrum include visible plus NIR. Visible plus certain part of infrared. They are combined together to form the optical spectrum. Okay. So the energy reaches to the sensor in optical spectrum with wavelength less than 3 micrometer. So we are talking about the wavelength less than 3 micrometer. As many times we discussed about the significance of 3 micrometer dividing line in a radiated energy versus wavelength curve. From a ground resolution, so there is a mention about a ground resolution cell, that is an area from where the energy is, where interactions takes place. So from a ground resolution, when energy interact with the ground resolution cell over here, it is further reflected or radiated back, and then it reaches to the, let's say, somewhere to the sensor. Let me redraw this again. Less than 3 micrometer. Okay. So we have a ground resolution cell over here, sun. So at a different point, there is incident energy. Somewhere here we have a sensor on board satellite. There is a mirror. So this energy passed through the mirror and then further it is interacted with the CCD, charge coupled device. That we'll discuss later. So there is a upwelling radiance. We call it upwelling radiance. And finally it reaches to the sensor. Okay. So when we consider the wavelength less than 3 micrometer, then the energy part, okay, which is reaches to the sensor, is constituted of what? Atmospheric.
Reflected energy.
Listen carefully. And if you recall, in one of the discussion, we talk about the effect of scattering as a hedge effect. Okay. So atmospheric scatters, when we consider the energy received at the sensor. So due to the scattering in the atmosphere, as we have already discussed before, there are the certain atmospheric scatters which also fall, which also goes through the mirror and reaches to the sensor. Because see, in scattering, if you see that this is the incident energy and then scatters are, they are in a different direction. So due to the atmospheric scattering, okay, we have a scatters component in the field of view of the sensor. So this option is atmospheric scatters, they are present. It is correct. We don't have a radiated energy because we are considering the wavelength less than 3 micrometer. So if you analyze, the Earth starts radiating energy after 3 micrometer. Fine. So this radiated is not correct. Reflected energy, yes. We have the reflected component because less than 3 micrometer, the energy that is the upwelling radiance, or after the interaction, the reflected energy is there. So this will also reach to this. Okay. So in the last option, we don't have a radiated energy. So the first option is correct. Okay. So there are the atmospheric scatters which are present in the total energy, total upwelling radiance reaches to the sensor. And this is the reason why, if you recall one of the discussion, I showed you two different images. In the first images, those were the photographs. In the first photograph, clearly you can see the terrain in RGB, while in the second case, you noticed one layer kind of thing, due to which the contrast in the image was decreased. Okay, and I told that this happens due to the addition of atmospheric scatters in the total energy reaches to the sensor from each ground resolution cell. Is it clear?
Yes, sir.
See, very carefully, you need to read the problem. All the like to solve the problem, just see that this can be a subjective problem, and you need to write all these concepts while attempting this problem. And very detailed, all the components we have already discussed in our class. Just you need to combine those concepts, you need to analyze it, and you need to arrive at the correct conclusion, correct answer. The 10th problem, and it is related to the spectral signature of water with respect to that is reflectance of water with respect to wavelength. So there we discussed that water only reflect energy within visible spectrum. Okay, out of the visible band, in the clear water you can't get the reflectance. So reflectance from the water is only there, and highest we get in green band. This is the blue. Then we have a green, and then finally we have a red. Now after that we have a IR band, infrared band, then microwave. It is 0. Okay, this is the reflectance. Water. What happens when you increase the turbidity? Like this is the water body. Okay. So in this water body, if it is clear water, then this curve you will get. This will be valid. Turbidity, increase in turbidity means the mixing of soil particle or sand particle. Then there will be the presence of some particles. Okay. And due to the presence of these particles, what will happen? You can expect a reflectance in near infrared band also. And even the overall reflectance will further increase. This plot can be to increase the turbidity. It will go like that. So where is the change which you can notice over here? The change in the reflected energy. And the reflected energy increases at each wavelength. So reflected energy from water increases. Transmitted will decrease. Absorbed will decrease. If reflected will increase, why it is so? Here you need to mention about a law of conservation of energy. Like when we talk, that entire equation you need to write. The incident energy EI, the part of energy is reflected back ER, then ET transmitted and EA. So there you need to write the incident energy is equal to ER plus EA plus ET. Normalize this. So 1 is equal to rho plus alpha A plus beta. Sorry. This is beta T, and this is reflected alpha R it could be. So when alpha R will increase due to increase in turbidity from this law of conservation of from this equation, because you see addition of these three is 1. What will happen? This will decrease, this will decrease. And reflected energy from water decreases. Obviously, it is not decreases over it is increases. This up. If it is a subjective problem, and there and it is expected you to write a justification. Then you need to write all these steps and you need to draw the curve and you need to draw this, and there you need to mention, okay, this is a air to liquid transmission. In air to liquid transmission, we have a both component, absorbed and transmitted. Okay, and these are the variables which gives you the ratio between absorbed and incident, radiated and incident, sorry, reflected and incident, and transmitted and incident. So I hope now you have understood, like in the next time when there will be the quiz and the questions will be like that. So how you can approach, at how much extent you need to analyze the problem. And very carefully, you need to, before the examination, you need to revise your notes. As I have already suggested you, while the discussion, you have already a notebook for that. You need to write it. And you can refer the videos. Again, you need to improve your notes. So once you read the books, once you see the videos, lecture videos, you have one notebook for this course where you can add the concepts which you feel that, okay, that should be written there.